Today's lesson is 1.4, transformations. We're going to go ahead and start with how to translate functions, and we're going to be using our quadratic parent function as a base. However, I can use this for any of my parent functions, including my linear, my square root, my absolute value, any of them, okay? So let's go ahead and take a look at our quadratic function. The parent function, of course, for my quadratic is the graph f of x equals x squared or y equals x squared. Let's go ahead and substitute in some values and get some points. So remember, if I do f of -3, that means I'm taking this -3 and I'm squaring it. Not only am I doing 3 times 3, but I'm doing negative times negative, which gives me a positive 9. Okay, f of -2 would mean I'm doing -2 squared. I'm doing -2 times -2, positive 4. And here's the last one that I'm going to show you the substitution completely. I'm doing -1 times -1, which is positive 1. So for the next one, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. Notice that there is a repeat. There's a pattern. Both of my 3's, both positive and negative, turned out to be 9. Both of my 2's, positive and negative, turned out to be 4 when I squared them. And both of my 1's, positive and negative, turned out to be 1 when I squared it. The only one that doesn't have a partner is 0, and that's because this is where my vertex will lie. Let's go ahead and place these points on our graph. 2, 1, 2, 3, 4, 4, and 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, what I can do is once I have 1, 2, 3, and 9 placed, I can go 1, 2, 3 to the other side, and there's my -3, positive 9, because they're both 3 away from the y-axis. This is that axis of symmetry that we were talking about. And I'm going to do the best I can to come in here and shape it like the letter U. There we go. Remember, the parabola itself is what the name of the U-shaped graph. That's the name that we give the graph. That is shaped like the letter U. And the vertex is my turning point on my parabola. And my vertex, of course, would be this point right here. There's my vertex, 0, 0. And remember that that vertex can be considered a maximum or a minimum, depending on the orientation. This one would be a minimum. This one would be considered a minimum because it is the lowest point of my graph. All right, let's go ahead and talk about transforming this, taking this parent function and moving it, okay? So the first thing that we're going to talk about are our vertical transformations. Our vertical transformations. Now, we could go ahead and we could erase this part right here, and we could replace it, we could replace this simply with our function g of x. So our original plus k, okay? In this case, we're going to do x squared, but you really could do any function. You could do any function. Notice that really the only thing we're changing is this part right here. This is the only part that we're changing. If k is greater than 0, that means, let me zoom in here. That means, of course, if k is positive, right? If we're bigger than 0, we are positive. Then my graph would be translated k units If k is bigger than 0, we're going to go up. If k is less than 0, these are going to be my negative numbers. And of course, remember when I add a negative, it actually looks like subtraction. Then I'm going to be translated the absolute value of k units down. Okay, so it'll look like -5, so I'll move 5 down. That's basically what it's telling me, okay? Let me change this back to my purple. Here we go. Let's take a look at this first graph. There we go. Sorry, guys. There we go. All right, so here's my graph. Notice that right here is my parent, and this part right here is my add-on of k. Okay, so what's going to happen? What is going to happen is that my graph is going to move. Now, you could see this movement through a table. So we could go ahead and create a table, much like they had for us with the original. There we go. And we could put in -3 and -2 and -1 and 0 and +1 and +2 and +3. Let me make that a little bit bigger. There we go. And we could come in here, we could just plug it in. -3 squared plus 3. That would be 12. Let me show you one more time. -2 squared, which is 4, plus 3, that would be 7. -1 squared is 1, plus 3 is 4. 0 plus 3 would be 3. 1 squared plus 3 would be 4. 2 squared plus 4 would be 7. And 3 squared plus 3 would be 12. There we go. There's our points. Let's go ahead and plot them. -3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. -2, 7. So remember, I'm just -2, +7. So I'm moving 1, 2 to the left. That's the -2. And then I'm going to go 1, 2, 3, 4, 5, 6, 7 up. That's the +7. I lost it. 1, 2, 3, 4, 5, 6, 7. And then -1, +4, up 4. 0, 3. So don't move from the origin, but go up 3. And then what's going to happen, remember, is they're going to mirror each other exactly through that vertex. Okay, this right here would be my vertex. How do I know? Because this is the only one without a partner. It's the only one without a partner. The one without a partner, the one that's all alone, that is going to be my vertex. So here is my graph. There we go. So how did it move from that graph on up above? Well, my K, which is my highlighted number, is +3. So I would say that this graph moves 3 units up. That's it. Move 3 units up. Let's try another one. Let's take a look at this graph right here. G of x equals x squared minus 3. So notice right here is my k value. This time k equals -3. We can always go back and do our table. We can always do a table. We can always do a table. And I'm just going to go ahead and put some numbers in there. So -3 squared minus 3 would be 6. -2 squared minus 3 would be 1. -1 squared minus 3 would be -2. 0 squared minus 3 would be -3. +1 squared minus 3 would be -2. +2 squared minus 3 would be +1. And lastly, 3 squared minus 3 would be +6. So once again, here is my vertex because this is the only one that does not have a partner. Boom, boom, 2. There we go. vertex, oops, vertex. Let's go ahead and graph those. -3 means from the origin right here, I'm moving 3 to the left, 1, 2, 3, and I'm going to go 6 up, 1, 2, 3, 4, 5, 6. There it is. -2 means I'm moving 2 to the left, and +1 means I'm going on 1 up. -1 and -2 means I'm going 1 down. 0, -3, and then remember they just match each other. Remember how they match? These two match. So since it's 1 away, there's 1 on this side. Since this one is 2 to the y-axis, there's 1, 2 on the other side. And then since this one is 1, 2, 3, there's 1, 1, 2, 3 on the other side. So this one I can graph pretty quickly once I have one of the sides completed. There we go. There's our graph. And if you go back and compare this to the parent, or if you use this rule, since my k is negative, I would say it moves my graph 3 units down. Okay, now take a look at where K was. Take a look at specifically where K was. K was always after the parent function. K is always after the parent. This right here is my parent function. So I can replace the quadratic with the square root, with the absolute value, with the linear. It doesn't matter. I can put any of the other 5 parent functions in there. If I go ahead and add a number after it, it's going to move my graph up or down. Plus is up, minus is down. That's basically what this tab in the foldable is telling you. All right, let's go ahead and look at the next one. This one is a horizontal transformation. And once again, we can generalize this. We can go ahead and generalize this. Let me go ahead and do this. I can take the square off. Let me go ahead and change it from f of x to g of x. There we go. Because that's what the foldable is asking. And so I could add the f of right here, and now it's just whatever my parent function is. But take a look that inside this parentheses is where my new number change is going to happen. Notice where my change is. It is inside the parentheses with the parent function. If my h value is greater than 0, if it is positive, then my graph will move 2 units to the right. If my h value is less than 0, if it is negative, there we go, then my graph will be translated the absolute value of h units to the left. Yes. Now be careful because this is correct. If h is positive, we move to the right. If h is negative, we move to the left. But I want to show you something. Let's say that h is equal to 2. Okay, so I have my positive h. Let's go ahead and plug that into this function. So my transformation g of x would look like f of x minus 2. Take a look at how it looks. It's positive, but it looks like it's negative. The graph is being very sneaky and kind of a little fake. It's wanting you to move to the right, but it's trying to trick you into moving to the left. Be careful. Let's go ahead and change h to a -2. I'm going to go ahead and plug that into the function. My new transformation now becomes, and take a look, whenever I have a double minus like I have right here, I'm going to change that to a plus. So once again, take a look. I'm a -2, so I need to move to the left, but when I look at the function, I'm positive. H is a sneaky number. H is tricky. It's a bit of a trickster, and it's trying to mess you up. Don't let it. You know what's happening. It's just the opposite of what it appears. Okay, if it appears to be positive, remember it's really negative and you're moving to the left. If it appears to be negative, it's really positive and you're moving to the right. Let's practice with our quadratic. All right, here is our graph. G of x equals, and notice again that my H is inside. My H is inside. Now, technically, I've highlighted too much, so let me go ahead and erase that. This right here is H. This, let me circle it with my blue. This is part of the formula. This is part of the form that I have, okay? So my H in this case appears to be -3, but it's really +3. Okay, it's really +3. I can go ahead and I can always do a graph, a table. And here's some numbers that I picked. And I picked these ones specifically. Ooh, I need some more space. Hold on. Squeeze it in there. There we go. So when I plug them in, I'm just doing 0 minus 3 squared, 1 minus 3 squared, 2 minus 3 squared, 3 minus 3 squared, 4 minus 3 squared, 5 minus 3 squared, 6 minus 3 squared. So notice you do have that pattern once again because it is a quadratic. The parent was a quadratic because of the square right there. And notice you do have your partners and there's your vertex right there. There's your vertex. Okay, let's go ahead and graph those. So 0 and 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 and up 9. 1 and up 1, 2, 3, 4. 2 and up 1. 3, 0. 4, 1. 5 and up 4. 6 and up 9. So take a look at the graph, and if you go back to the very top flap of your foldable, you can see that this from the parent function, it's gone from the vertex and it's just shifted the vertex over 3 points. And so I would say that this one has moved or moves 3 units right. Okay, I can see that from the graph, but I also knew that that was going to happen because my H is positive. Remember, when my H is positive, it looks like it's negative, so I know it's going to move to the right and not to the left. Let's take a look at another one. Here is my H. Here is my H, but this time, if I look right here, this has changed. This has changed. And so now I'm going to grab it as part because I know that H is really -3. Because the only way to change that minus that is part of the formula, this minus right here, which is part of the formula, is by making a double negative. So H has to be negative. From that, I already know how my graph is going to move, but remember, you can always go ahead and do yourself a table, and here are the points that I would put in this table. And I'm choosing these points so that I can see the vertex, because I know you're thinking, but you used these other ones the last time, Miss. And the reason I'm doing that is because I want to be able to see that vertex. Okay, so there we go. And once again, notice because of the square, this is the beauty of the quadratic. I have that I have that axis of symmetry. And so I should see the double up of my numbers here in the y value so that I can find the vertex right here. So there's my vertex. And then from the graph, I can see this movement. From the graph, I can see this movement. So negative 6, 1, 2, 3, 4, 5, 6 to the left, 9 up, 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 5, 1, 2, 3, 4, 5, 1, 2, 3, 4 up. Negative 4, 1, 2, 3, 4, 1 up. Negative 3, 0. And then I can just do my there we go. Use my axis of symmetry. This time my axis of symmetry would be going through my vertex and look 1, 2, 3, 1, 2, 3. That's how I could do it. That's how I could graph it so fast. And if you go back and look and compare this to the parent function, it has simply taken the vertex here at 0, 0. Remember the parent function had the vertex right here at 0, 0, and it has shifted it over 1, 2, 3 units. So I would say it has moved or moves 3 units left. And you can actually see the movement to the left. Okay, don't let H trick you. H is pretty sneaky, pretty tricky. And so please just make sure that you really take your time when you're looking at H. The difference, once again, between H's K is their placement. H will always be inside the parentheses right next to the variable X, and K will always be added on after the parent function. Okay, so you need to see the full parent function, and then we're going to add K on after. All right, the last thing we're going to talk about are three different transformations, one called stretching, one called compressing, and one called reflecting our function. So let's go ahead with the stretching. And of course, remember, we're talking about our quadratic parent function, but we can do this with any of them. When I am talking about stretching my parent function, if the absolute value of a is greater than 1, then my graph of my parent function is a vertical stretch. Oh, wait a minute here. Hold on. There we go. Then the graph of the parent function, f of x squared. So notice where my vertical stretch is. It's this number right here. And what that number is doing is it is being multiplied in front of the parent function. And of course, remember, our parent function this time is x squared, the quadratic, but you could replace that with simply x, the linear, or the absolute value of x, but it's got to be outside, okay? So let's take a look at this first graph here, 2x squared. So notice right here, where is it? There we go. Notice right here, here is my stretch. Here is my stretch. Okay, let's go ahead and we can plug these numbers in. Negative 3 for x, negative 2, negative 1, 0, 1, 2, and 3. And we're simply going to do 2 times negative 3 squared, which is 18. 2 times negative 2 squared, which is 8. 2 times negative 1 squared, which is 2. 2 times 0 squared, which is 0. 2 times 1 squared, which is 2. 2 times 2 squared, which is 8. And 2 times 3 squared, which is 18. Now, what's going to happen here for your a value? These, since they are greater than 1, the absolute value, they are going to mainly be seen as whole numbers. 1, 2, 3, 4, 5. Or you will see them as mixed fractions. Like 5 over 4, 6 over 5. where the numerator is a little bit bigger than the denominator. If I go ahead and graph this one, let me see. I'm going to go by twos, so I'm going to say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and the top would be 26. And then I'm simply going to go by ones. So I have -3, 1, 2, 3, and 18. And then I have -2, and I have 8. I have -1, and I have 2, 0 and 0. And then I have the same on the other side. There we go, something like that. And I just made that y value go, that y-axis go up by 2 so that I could actually see the whole thing. What I could say about this one, if I had to write it in words, which is what you're going to have to do for me today, you would say that this is a vertical stretch by a factor of 2, which is that number that I highlighted. Okay, let's go ahead and look at a compression. A compression. If I am compressing my parent function, the absolute value of a is going to be less than 1. The graph of the absolute value of the a times the parent function is going to be called a vertical compression. Now, the types of numbers that we're going to be seeing here for a are going to be fractions. This time, when we look at this variable a here, when a becomes a number and it's being multiplied by the parent function, then it is going to be a fraction of some kind. It's going to be a fraction of some kind. So let's take a look at this one right here. Notice my a this time. My a has become something different. Let me go back and that in. My a has become a fraction this time. 1/2, 2/3, something like that. I'm going to go ahead and take a look at these numbers. So when I plug in -6, I get +18 when I plug it into the function. -4, I get 8. And I'll show you guys how to use the calculators to get this table. So you don't have to worry. You can use your calculator to get your table, and I'll show you how to do that. 2 is 2. 4 is 8. Remember, a good table would not contain fractions in X or Y. They're easier to graph than, whole numbers are easier to graph. So what I'm going to do is I'm going to go ahead and go by twos again on my X-axis, my Y-axis. So I'm just going to go ahead and put them in. 10, 12, 14, 16, 18, 20, 22. And then I'm going to go by twos down here as well, just so that everything will fit. That's the only reason I'm choosing to do this. So -6, +18. There we go. -4, +8. -2, +2, 0, 0. +2, 2, +4, +8, and +6, +18. There we go. This time, if I were to describe this graph, I would call it a vertical compression by a factor of and it's going to be that highlighted fraction, 1/2. So I'm picking a compression because it is a fraction, and I would be picking a stretch if it is a whole number, okay? All right, the last one is my reflection. And sometimes instead of using the word reflecting or reflected, we see this word flipped. Okay, so I would add this to the outside of that foldable that you have. I'm going to call it flipped sometimes, or sometimes you'll see it's reflected, or it's being reflected, or it's reflecting. Okay, if A is smaller than 0, the graph of, and take a look once again, let me pick a different color here. Let me go to my pink. We still have this A, and we're still talking about the same A, but it's a little bit different this time. Oh, no, here. It's still being multiplied by my parent function, but it is called a reflection across the x-axis of the parent function f. Okay, so we're going to be reflecting across the across the x-axis. Here are going to be my numbers that I'm going to plug in. Notice right here, here is that flip. Notice the flip, because if you noticed at the beginning, A is less than 0, so A is going to be negative. A has to be negative. So -3, it would become -9 because this time I plugged in this. This is what I actually plugged in. So notice I have that double negative. -2, I'm going to get -4. -1, I'm going to get -1. 0, I'm going to get 0. 1, I'm going to get -1. 2, I'm going to get -4. And 3, I'm going to get -9. Take a look at what my graph looks like. -3, 1, 2, 3, -9, down 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. Let me erase that other one because that's not correct. -2, 1, 2, 1, 2, 3, 4 down. -1 and 1 down. 0, 0. There we go. Take a look at what my graph did. If you go back and look at the first foldable and you look at the parent function, remember the parent function is just like this. Basically, I've taken this letter U and I flipped it over the x-axis. Right? I flipped it right here over the x-axis and created an upside down letter U. This one, I would describe this as a reflection across. Sometimes we use the word over the x-axis.